thanks for the opportunity to talk about my research. This is one of the subjects I have worked on, and I will try to give you a very simple idea of this subject, non-technical one, I hope. So my subject is about superconductor or superconductivity. So let me first remind you what is superconductivity. Superconductivity is about electrical resistance. So electrical resistance exists for all of the conductors we use, like this wire. And when you run electrical current through it, it will generate heat. This can be sometimes useful. Well, we use it to heat up things. But most of the time, it's just very wasteful, like my computer does. It wastes the electrical energy to generate unwanted heat. So the one source of this resistance comes from imperfections of a material. You may think we can never completely get rid of it. However, exactly 100 years ago, Pappalardo discovered the so-called superconductivity. He cooled the mercury down to very low temperature, 4 Kelvin, or minus 450 degrees Fahrenheit, and measured the resistance, and see the resistance suddenly drops to 0. And this led to his Nobel Prize 2 years later. So one message I want you to take is superconductivity is about zero resistance. This happens below a particular temperature we call transition temperature, and this happens despite there's imperfections in the material. So we have this wonderful phenomenon of superconductivity. Is that really useful? Yes. Superconductors have been used to make very powerful magnets. This has been used from large machines like a Large Hadron Collider to small machines like the MRI machines in hospitals. And it also has many other promising future applications like magnetic levitation trains or power grids. However, there's one important property we have to improve on superconductors to really use them. That's the transition temperature. That's a temperature below which we have no resistance. Let me show you some simple examples of the typical transition temperature. This is the first superconductor, mercury, transition temperature of 4 Kelvin. And these two are so-called high-temperature superconductors. As you can see, the transition temperature are still very low, minus 300 degrees Fahrenheit yet. It's nowhere close to the typical temperature around us, or even in your typical refrigerator. So if we want to use them, we have to use very special refrigerators, which is inconvenient and very costly. So of course, we want to improve that. And in fact, we want higher and higher TCs. Let me briefly review the 100 years history of TC. So as I said, the superconductivity was discovered 100 years ago by Pappalardo. The temperature at that time is about the boiling temperature of liquid helium, 4 Kelvin. And for the next 7 decades, transition temperature slowly increases. These superconductors are mostly metals or metal alloys. They are so-called conventional superconductors. Well, from here, you can see the curve doesn't look very promising. This changed dramatically 25 years ago. There was a discovery of the so-called copper-based high-temperature superconductors. You can see the transition temperature jumped. Well, I should say a factor of 5, but it's very impressive that it raised above the liquid nitrogen temperature, which is important for us because above this temperature, we can cool these materials using much cheaper refrigerators. So let me summarize about this copper oxide superconductors. It's discovered 25 years ago by Biden-Mills and Mueller, which led to Nobel Prize just 1 year later. And I think the most amazing thing about these superconductors is not about their high TC. It's actually from a materials science point of view. So we typically think to get a superconductor, we should use good metals and cool it down. However, these copper oxides are very different. We get those superconductors by slightly changing the chemical composition, we usually call doping, and we dope an insulator, which doesn't conduct electricity. Once we slightly change the chemical composition, it turns into a superconductor which conducts electricity perfectly. This, I think, was conceptually very shocking and completely changed the paradigm of superconductivity. And also, this transition temperature is very high above the liquid nitrogen temperature. Okay, for the last 2 decades, people think this property, although sounds very unnatural, maybe is the key to high temperature superconductivity. This paradigm, again, was changed 3 years ago by the discovery of iron-based high temperature superconductors, which are shown here. It's first discovered by the Japanese group led by Professor Hosano, and the transition temperature quickly increased, well, not as high as the copper oxides here, and still even below the liquid nitrogen temperature. But I think it's an important discovery in that, again, it changed the way we think about high temperature superconductivity. So this time, we are not changing an insulator into a superconductor. We are still changing metal, but not a very good metal. We call it semi-metal. And this opens up a very broad area to look for superconductivity. If you only think only insulators can be turned into a high-temperature superconductor, there's only a very small fraction of the known chemical compounds we can do that. But this time, with the discovery of this iron-based superconductor, we know that it's possible for many other materials we can get high-temperature superconductivity. And, well, the research effort was very intense initially. Within 2 months, the transition temperature doubled. And I think this really rekindled the enthusiasm for higher TC superconductors. So let me briefly introduce 2 basic properties of the iron-based superconductor. First, as I said, it's a metal, semi-metal. It's a conductor. As you can see, this is measured resistance. The blue curve and the green curve are the basic materials without chemical manipulation. The resistance decreases with temperature, which is typical for metal. It's not a very good metal. It's semi-metal. Loosely speaking, it's a bad conductor. This is very different from the old high-temperature superconductors, copper oxides, which are insulators. However, the new high-temperature superconductor, iron-based one, has a similar property to the old ones. They have a magnetic order. Lou has talked about this concept before, but let me remind you. The electrons carry not only charge, electric charge, also carry another property called electron spin. It's like a little bar magnet. For my purpose, it's better to think of this spin as 2 species of electrons. One of species is such that the bar magnet spin pointing to the north, and the other species pointing to the south. And in these materials, the electron spins form some regular pattern, like in this one, the copper oxide, and this is one of the iron-based material. They form this staggered pattern, which we call the antiferromagnet. So we have these 2 properties. One, for the iron-based high-temperature superconductor, one of them is different from the old one, old copper-based one. One of them is similar to the old one. You may ask, which property is essential for high TC? I think anybody, without doing theory, would guess this latter one, the common property, is important for high TC. And this, well, I should say, is indeed the finding of our theory. So our finding is probably not that surprising, but I think it confirms this common sense. So now let's turn to theory. The basic ingredients of superconductivity is the so-called Cooper pair. In superconductors, we know due to some attraction, 2 electrons pair up, form one object we call the Cooper pair. Once they pair up, some of the properties changes. They change from fermion to bosons, and those pairs, they behave like bosons, and at low temperature, they can do this Bose-Einstein condensation, and this gives us superconductivity. I will not go into too much detail about this side of the theory, but if you think about this, if you scratch your head a little bit, you will see it's actually paradoxical. Why? 2 electrons, they carry the same electrical charge. By Coulomb's law, you learned from the first electromagnetic course. The 2 particles with the same charge, they should repel each other. So where does this attraction come from? Why can they pair? So this question is actually the central question for all theories of superconductivity. So how can we answer that? Again, let me show you how we answer that in our old successful theory of superconductivity, the BCS theory. This was developed by Badin, Cooper, Schrieffer about half a century ago. And they say the attraction, effective attraction, was mediated by the motions of ions. So I think everybody knows in solids, we have not only electrons, we have ions around. They form a regular pattern called a lattice. This is a simple picture of the lattice. And imagine one electron comes by, and because the electrons carries opposite charge to the ions, it will deform the lattice. The electrons move fast. The ions are heavy. They move slowly. So this electron go away. However, this deformation remains for some time. So now another electron comes by. It will be deflected by this deformation. And this is, in some sense, an effective attraction. As you can see, this effect, you can imagine, is usually very weak. Doesn't give you very high transition temperature. And indeed, we know that this cannot explain the superconductivity for the so-called unconventional superconductors, including the copper and iron-based high-temperature superconductors. So we need some other theory. So what's the other theory? In other theory, we only have electrons, but we know the electrons repel each other. First, we have to satisfy this repulsion, make them happy. How can we do that? Let's imagine we have two electrons and two positions. They repel each other, so they don't want to sit on top of each other. So they occupy different seats. There are still two possibilities. As I said, we have spins for electrons, or in some sense, two species of electrons. There are two situations. There are two electrons of the same different species, or two electrons of the same species. You may think, well, maybe only the electrical charge is important in this property of superconductivity, so these two situations are equally good. Actually, that turns out not true. What happens is there's a very important low-energy effective interaction we call the spin exchange interaction. It happens this way. So these two electrons don't like to sit on top of each other, but still electrons like to move by quantum mechanics. So one of the electrons will try to move to the other seat. Well, they are not happy, they sit on the same seat. But they can move forward. By moving forward, this electron goes back to the other seat. During this process, you can see the two species exchanged. Well, you may think, well, this latter situation, same species of spin can also do this. Let's imagine this electron also move to this seat. Why can't they do that? Turns out they can't really do that. This is because Pauli exclusion principle. It says two electrons cannot have the completely same properties. They cannot have the completely same spin and same positions. So this process is blocked. So you see there's a subtle difference between the top and the bottom situation. So for the top one, the electrons don't like to be on top of each other because of repulsion, but still they can move around. The bottom one is completely blocked. They cannot move. So in some sense, the top situation is favored. It has lower energy, and this gives us a small effective attraction between electrons of different spins. We usually call it spin exchange interaction. And this gives us, first, this regular pattern, staggered pattern of these spins, the antiferromagnetism. And in certain cases, it will also cause pairing. Usually in this way, it's a pairing between the opposite spins and on neighboring sides. Okay, so now we know one scenario that by subtle quantum mechanics, quantum mechanical effects, we can have small effective attraction. However, from this large repulsion and the quantum mechanics, at low energy, there's many other possible interactions. How do we deal with that? Let me look at the effective interaction by another perspective. The interaction between electrons is about how electrons scatter off each other. And for this so-called low-energy effective interaction is typically the interaction mediated by some high energy electrons between the low energy electrons. I will loosely call them fast and slow. So let me show you a very naive picture of how this happens. We have several electrons around. These two electrons move slowly. Another electron of higher energy, it moves fast. It scatters off those low energy electrons, change their directions, and this, in effect, mediate interaction between these two electrons, low energy electrons. How do we characterize this? And we have a systematical way to compute this effect, which we called renormalization group, which is very technical. I will not go into any detail of that. Its basic picture is just as simple as this. We compute the effect of higher energy electrons to low energy electrons. And in this process, we can compute the effect of all of the high energy electrons without any particular bias. This has a long history I will not really talk about. So let me show you our results for this iron-based materials. For these iron-based materials, due to their particular material structure, turns out the electrons in this material favors to either this staggered pattern or that staggered pattern. The spins form either vertical or horizontal stripes. And if you look at these two pictures, you will see for the nearest neighbor, there's really no preference whether it wants to be the same or different from the central spin. But for the second neighbor, it favors definitively the opposite spin to the central one. So this property leads to, first, strong effective spin exchange interaction between the second neighbor, and a strong pairing tendency between the second neighbor. This, I should say, is the main result, in some sense, of our calculation. It tells us that the shape of the Cooper pair, if we look at it in this real space simplified picture, is mainly between the second neighbor sites. And our physicists, condensed matter physicists, usually work in momentum space. In momentum space, this tells us the wave function of a Cooper pair transcends in momentum space around different Fermi surfaces. Fermi surfaces are positions in momentum space where low energy electrons reside. So you may think we have solved the problems of iron-based material. Not quite. There are still many challenges, many experimental challenges. So we have our theory and actually many other theoretical groups found this particular pattern of pairing. How can we detect that? This turns out to be quite non-trivial. Actually, we proposed some indirect way to look at it by using scanning tunneling microscope to look at the sample surface and look at, in some sense, electron ripples on sample surface. By the momentum, well, the wavelength of the ripples, you can get some information about the sign of the Cooper pair wave function. And we proposed that, and I was quite surprised that the experimentalists really detected that later. And I should say, still, a direct measurement of this shape of a Cooper pair or Cooper pair wave function is lacking. We are still thinking of a better way to do that yet. And I think a more challenging question is how to confirm this proposed pairing mechanism. The pairing really comes from this magnetism. This, I don't think anybody has a clear idea yet. So I think a more practical, important question is where do we find other high-temperature semiconductors? From this lesson we learned in both copper-based and iron-based materials, we know that magnetism looks like important in this semiconductivity. So maybe we should study other magnetic materials. And here at MIT, with Professor Santil in the back, we studied one particular magnetic material, the strontium iridium oxide. And we realized that its electronic structure is probably quite similar to copper oxide. If we can chemically manipulate that, maybe we can realize high temperature semiconductivity. This is still ongoing collaborations with many experimental groups, including Professor Neil Gedich's group at MIT. So now, let me summarize what we have now. The superconductivity, in particular, high-temperature superconductivity has been a century-long quest for condensed matter physics. In the last few years, we discovered a new family of high-temperature superconductors based on iron, and this broadened our field of high-temperature superconductivity and changed our paradigm for high-temperature superconductivity. And based on our study, we suggest first a particular form of pairing, and we suggest the mechanism is related to magnetism. And with this basic understanding, we continue to look for other potential high-temperature superconductors. So now, let me say one word about the fellowship without approval. As a student, I learned this statement: physicists by nature are happy. However, here at MIT, under this Pappalardo fellowship, that's proven wrong. So this really thanks to Neil and Jen, and thank you all for your attention.
Thank you, Fa. We'll have a number of questions and comments, I'm sure, but let's begin with you.
What exactly happens when you reach that critical temperature? Is there a phase change, or is there some event that happens that causes it to become a superconductor under the temperature, but above it?
Okay, various things happens. Actually, in different superconductors, this transition can happen in different ways. But in the conventional superconductor, what happens at that, most important thing happens at that temperature is, above that temperature, we have a Fermi surface, meaning you can excite electrons with arbitrarily low energy. That's a surface, usually a surface we draw in momentum space. Below that temperature, all of these properties are lost. All these low energy electrons are lost. We call a gap opening. And this opening of the gap around the Fermi surface is, I think, the main ingredient of the old BCS theory. Besides that, the structure usually don't have a significant change. There are some change in specific heat, for example, and other thermodynamic properties, but I don't think those are really very essential for this property. The most essential property is the electrons form a pair, they bond, so it will cost energy to really extract a single electron. That's the energy gap. And those pairs, they both condense, form a coherent superfluid in some sense. Those can conduct electricity without resistance.
It's as if the electrons undergo a phase transition. They could kind of move, roughly speaking, kind of like a liquid or a gas in a disordered way until you reach that critical temperature when suddenly at least one aspect of the electrons freezes into a macroscopic quantum state of these pairs. And then the electron wave function of these pairs just moves in lockstep. So, other questions or comments? I want to ask about, I should say first of all that I was very impressed with the way that you took what I know are quite technical calculations, yes, and try to express them into very simple pictures. And sometimes in doing that, you run the risk of oversimplifying the pictures. Mm-hmm. So I wanted to just ask you about the pictures because they're so pretty. One is this second nearest neighbor pairing, which gives you this diagonal interaction of the pairs relative to the lattice. Is that, so two questions about that. First of all, is that related to the D-wave nature of the pairing state?
Oh, you mean this one for the iron-based one?
Yes.
The iron-based, most theoretical group, and I think most experimental evidence suggests it's not D-wave. It's actually a particular S-wave. We usually call S plus minus, meaning if you look at this picture, this is a zero momentum. If you rotate this picture by 90 degrees, it doesn't change. So in that sense, it's S wave, but it changes sign in momentum space. The wave function changes sign in momentum space.
Okay. I didn't understand entirely about the sign change, but we can talk about that afterwards. The other question is that you've emphasized these interactions of rather nearby electrons. And in the BCS state, those electrons, in fact, that pair are widely separated.
Yes.
Are the interactions really close, or is this just a cartoon?
This is a cartoon and probably good for copper oxides, which are strongly interacting materials. We believe the iron-based one is something in between. It's neither too strong or too weakly correlated. So, but still, the measured coherent length, measured size of the Cooper pair is quite small, actually. Only a few lattice spacing.
Okay. So the test of your theory would be to calculate this coherence length and also the strength of the interaction, and then make predictions that the experimentalists could test. Is that possible?
Okay. You probably know, well, if you know the history of high-T superconductivity is typically calculating TC is very hard. TC, exponentially depends on the strength of the interaction, the attraction. So calculating that is usually very hard. I don't think any theoretical group around the world has succeeded in calculating TC for these materials. We have some rough estimate. I think it's probably of the same correct order of magnitude from the strength of a magnetic interaction.
And how about the coherence length?
The coherence length is not yet theoretically confirmed, I should say, because first, that depends on the detailed electronic structure. We don't have a very good, consistent theoretical calculation for electronic structure, which exactly match the experiment yet.
You have one more year of your Pappalardo fellowship.
Yes.
Are there other questions or comments? Howard?
I've got a very, very naive question.
Mm-hmm.
You're spending a lot of energy trying to understand what's going on in these superconductors with the goal of being able to figure out what other materials might work at a higher temperature, right?
Yes.
When Edison was trying to find the filament in a light bulb, he didn't care about theory. He just tried thousands and thousands and thousands of materials.
Yes.
Are people doing that? Why aren't people just trying materials and saying, let's not worry too much about the theory?
I think many people in other parts of the world are trying that, not in the States, unfortunately. Probably, I don't know, for whatever reason, funding or whatever reason. But in fact, this iron-based material was discovered by such a thorough search by this Japanese group led by Professor Hosono. I heard they have very large group of graduate students. They divide the periodic table into several parts, and one student studies.
Both the theory and the experiment here sound like a great reason to continue funding and research in this area. Let's thank Fa again.
Thanks.